the first thing I want to ask you, I want you to take 10 or 20 seconds. I want you in your own words to either write it down or think about what is dynamic equilibrium. What does that mean? And I know that's complicated, but I want you to write it down or you can just think about it. What does dynamic equilibrium mean? Does anybody have an explanation in their own words of what dynamic equilibrium is? Scott?
Where the amounts of everything stay the same, but the particles themselves are actually changing.
Yeah, so I think that's a fantastic definition. So the amounts are staying the same. Now, I want to be very clear, that doesn't mean we have equal amounts. Doesn't mean you have to have 5 of these and 5 of these. It just means that whatever amounts you have are not changing, right? The size of your crystal isn't changing. It doesn't mean there's equal amounts in the crystal and in the solution. So it's amounts staying the same or they're unchanging, but the actual particles are still moving or reacting. And we used an example, we used kind of an analogy of people entering and exiting the classroom. I want to make a different example, and because I'm such a crap artist, you get the joy of watching me draw a picture. Imagine there's a person in a boat, and the boat typically, hopefully this makes sense, is in water. And there's a tiny little hole in the bottom of the boat. Now, is this a situation that you would be happy with? Probably not. Hopefully not. What's the problem with this situation? Yeah, the water's going to start coming in the boat, and eventually what's going to happen? Yeah, it's going to sink. So you've got 2 options, okay? What are your 2 options? The engine's dead, and you've lost your oar, so you're not going anywhere. Okay, so you can't move. You're in the middle of the ocean. Even if you could move, whatever, it's not going to happen. What are your 2 options? Plug up the hole, right? So if I plug the hole, so there's water starting to fill inside the boat. If I plug up the hole, then we would start maintaining what we call a static equilibrium. If you plug up the hole, is the amount of water inside the boat and in the ocean, is it going to stay the same? Like, if I plug up the hole, the amounts of waters are not changing, right? Would you agree with that?
Yeah.
Perfect, okay. That's what we call a static equilibrium, because the water that's in the boat is going to stay in the boat. The water in the ocean is going to stay in the ocean. What's your other option? Instead of plugging up the hole, what else could you do?
Start bailing it out.
Start bailing out the water. Do you understand what that means? Yeah, can somebody describe for me what bailing your boat out means? People are making the hand movements, but Jada?
Like bucketing it out, like taking the water from inside your boat and putting it outside the boat.
You're gonna take a cup, right, or a bucket or something like that, and you're gonna scoop some water, and you're going to shove it out the other side of the boat. And so what's going to happen is Mr. Walton, first of all, he's an idiot, okay? So he took his boat with a hole in it out onto the ocean and didn't realize it. And so he's going to start bailing out his boat. So he's going to take the water from the inside of the boat and he's going to chuck it overboards. Now, sooner or later, if Mr. Walton is competent enough, he will reach an equilibrium where he's able to shovel out just as much water as is coming in. Does that make sense? So, is the amount of water inside the boat staying the same? Is it the same water all the time?
No.
No. Does that make sense? That's the difference between a dynamic equilibrium and a static equilibrium, where the amount of water entering the boat and the amount of water leaving the boat are identical. The rate of water leaving and the rate of water entering is the same. And so there's in effect no change in the amount of water. That's exactly what we have in our three situations. In our chemical reaction, we've got two opposite chemical reactions. And you will not establish equilibrium until what? Until both of these rates are the exact same. For every 5 of these you make, you have to break up 5 of those. Does that make sense? It's all about the rates of the chemical reactions. We don't actually care if there's 1 million of these and 1 million of those. That doesn't mean anything in an equilibrium. It's the rate of this and the rate of that. So how fast they're happening. The rate of crystallization and the rate of dissolving, the rate of evaporation and the rate of condensation. And just always keep in mind we do need a closed system for an equilibrium. It's not always necessary, but in effect you need a closed system. We're going to skip this for a second and maybe we'll come back to it. Let's get kind of an idea of what an actual equilibrium looks like. You made an equilibrium yesterday, and then you disturbed that equilibrium. Now, my bottle, I stole from somebody. I don't know, I can't remember whose group I stole it from. I think it was Isaac's group. But your bottle didn't look like this. This bottle's been sitting around for so long that it started to decompose and turn into some gross yellow product, okay? But would you agree, yesterday, when we took this and we shook it up, you got some sort of a disturbance in the equilibrium. Now, what happens slowly over time here?
The color changed to colors.
Was that exactly, I mean, minus all the yellow grossness of the color, right? Would you agree this is the exact same thing you saw yesterday? Yes. So what's happening is right now, I can tell we are at equilibrium. We're at equilibrium because the amount of oxygen leaving is the same as the amount of oxygen entering our solution. How can I try to dissolve way more oxygen right now? What's one way to do that? By shaking it up. If I shake this up, we're mixing the water and the oxygen above it, and by shaking it up, we're introducing that oxygen into the water. By introducing the oxygen into the water, we get a certain chemical reaction. Now, as the oxygen starts, there's way more oxygen inside the water right now than there should be. So it's going to start leaving more than it's entering. And it's going to leave and leave and leave more than it's entering. And sooner or later, the amount of oxygen in the water is going to get less and less and less and less and less until we reach equilibrium again. How do you know that we've reached equilibrium again in here? Yeah. So in the middle, right? I'll shake it up a little bit more. Have we reached equilibrium right now? No, because we can still see the color's not staying the same all the time. The color's changing. It's getting lighter and lighter and lighter and lighter and lighter. And now we've pretty much reached equilibrium. There's no more color change. Once the color stays constant, we've reached equilibrium. Isaac.
So
Okay, if we're not shaking it up,
Yeah.
Is the oxygen doesn't naturally want to? It's not going to dissolve in the substance. So
A little bit of it will.
a little, just a little
Yeah.
bit.
Yeah,
Okay,
a
so it is
little bit.
actually a dynamic equilibrium.
So it is a dynamic equilibrium
Right.
because, yeah, like, does oxygen normally dissolve in water?
No.
A little bit
Oh, yeah,
does,
yeah, yeah.
right?
Yes.
Because what lives in water that has to use oxygen?
Yeah.
Fish, right? So we do know, for sure, you know that there's at least a little bit of oxygen in water all the time,
Okay, yeah.
right?
All right.
Yeah. Here's the chemical reaction. And what we have going on here, we can just look at the descriptions of this. So initially, hydrogen is in excess, and iodine are added to the flask. So we've got hydrogen molecules, we've got iodine molecules and hydrogen molecules, and they've got the pictures of what the two kind of are being modeled as right now. So there's iodine, and there's some hydrogen in here, and iodine gas has a really nice, beautiful purple color to it. So that's why our bottle is colored purple. Now the hydrogen and the iodine, they can react with each other. When the hydrogen and the iodine react with each other, they make hydrogen iodide. When they make hydrogen iodide, there's less iodine gas than there was earlier. So here we've got how many iodine molecules here? 3. And when this molecule reacts with that molecule, all of a sudden we've got only 2 left. Okay, so what's going to happen to the color of our flask as we use up some iodine? Yeah, it's going to start to become a little bit more colorless. And that sounds stupid. Okay, a little bit more colorless is oxymoronic, but hopefully you understand what I mean. Early in the reaction, hydrogen and iodine form hydrogen iodide. Hydrogen iodide is colorless. It has no color. But it doesn't matter how long we wait. It doesn't matter how long we wait. If we wait for 50 years, this bottle will never, ever, ever become totally colorless. It will always have a little bit of color. And that's because every once in a while, these hydrogen iodide molecules will split up to make hydrogen and iodine gas again. Does that make sense? So we're going to write out the chemical reaction that's happening here. This is just at the bottom of your page, right? The chemical reaction taking place in this flask is hydrogen gas is reacting with iodine gas, and it's making hydrogen iodide. Now there's a couple things wrong with the equation that I just wrote down. One thing should really stick out in your mind, hopefully. Every chemical reaction should always obey 2 laws. Does anybody know what those 2 laws are? Sky, give me one. The law of conservation of mass. You cannot destroy matter, right? If you've got 2 hydrogen atoms at the beginning, how many do you have to have at the end? You have to have 2 hydrogen atoms at the end. What's the other law, just for academic purposes, what's the other law that every chemical reaction has to obey? Isaac?
Making sure the charges are balanced.
Yeah, the law of conservation of charge, right? So if you have a total charge of +1 at the beginning, you better have a total charge of +1 at the end. That's not going to come into play for a little while, but we do need to pay attention to that. Okay, well, this doesn't really show the full picture, because if hydrogen and iodine can turn into hydrogen iodide, what did I say hydrogen iodide could do? Jaden?
Turn into hydrogen and iodine.
It can turn back into hydrogen and iodide. So the way we represent that is either with a double-headed arrow or with this equilibrium arrow. So I'm just going to go ahead and erase that and put it back up. There's a forwards and a reverse reaction going on here. And remember, like we said yesterday, it's okay if you write this. That's perfectly fine, just 2 double-headed arrows. The double-headed arrow indicates that there are 2 reactions happening at the exact same time. What's the most obvious reaction you see here? Probably the forwards direction reaction. Hydrogen and iodine make hydrogen iodide. Just like we had earlier. But there's also a reverse reaction happening as well. What's the reverse reaction that's happening? Yeah, it's the exact opposite of this process. There's two hydrogen iodides turning into hydrogen gas and iodine gas. That's supposed to be an arrow. I know it looks bad, but that's supposed to be an arrow. Okay. So this last question is, what are some ways that we can identify that the equilibrium has been established? Think about this. What was the main way that we identified that equilibrium was established in this reaction? Yeah. So as the color was changing, was that equilibrium? If the color is still changing, is that an equilibrium? No, it means that we've got different amounts being formed, right? Once the color is constant, a few other things, not necessarily for this reaction, but there's some other ways that we can tell as well. Color's not the only thing you can measure. You can also measure pressure inside a container. So once the pressure is constant, now that wouldn't work for this reaction. We'll talk about that later. And if the temperature is constant, that's another way we can tell. That's another way we can tell we've reached equilibrium. If you allow two things to react together, and then once the color stops changing, or once the pressure stops changing, once the temperature stops changing, then you know you're at equilibrium. What about mass? Could you measure the mass, and once the mass stops changing, could that be an indication that you've reached equilibrium?
Well, the mass would never change, though.
The mass is literally never going to change, right? Especially in a closed system. Because whatever we make in here is trapped in the bottle. Those atoms are still trapped in the bottle. So if I measured this and it weighed, let's say 500 grams, as soon as I shake it up, has any mass left the bottle? No, it's still 500 grams, even though it's changing, right? We're not at equilibrium, but the mass is going to be the same. So that's there's a couple things going on there. What we want to do, we'll come back to this here in a second. We want to model equilibria right now. And again, because our classes have changed a little bit dramatically over the last couple of days, we've had 5 or 6 people kind of enter and exit. So I don't know if I printed off enough of these because I printed them off yesterday. Unless I have extras. Oh, look at that. No, I've got one extra. Woo! Perfect. So what we're going to do is we're going to model equilibrium with Legos. Okay. So what's going to happen is out in the lab there's 10 sheets of white paper that are just either sitting on the lab bench or they're sitting on the side benches, okay? Now, I've never done this activity because Newton and I came up with this activity. We thought it up last week and we're gonna take a stab at it, okay? We're just gonna let the dice roll and we're just gonna see how the cookie crumbles and all sorts of other metaphors. what's happening here is we want to model the chemical reaction of two identical, I mean, I know they're different colors, but hopefully you can understand these are identical pieces, right? Right? This is a 2x2 Lego square. This is also a 2x2 Lego square. Are we good with that? I'm not rich enough to buy single color Lego pieces, so I apologize. We're going to model the chemical reaction. This plus this makes that. Okay, thank you for being patronizing. So, that's half the reaction. That's in the forwards direction. What's in the reverse direction? Taking them apart. Ooh, wow. Okay, perfect. So what's going to happen? In this lab, we're going to be modeling a simple chemical reaction. The reactants turning into products, or are turning into P. We will use Lego pieces to simulate our reaction. When Lego pieces are together, they represent the reactants. No, they represent the products. I got to change that, I think. Yeah, sorry. They are the products. P. Always proofread your work. When Lego pieces are broken apart, these are your reactants. Many reactions can proceed in a forwards direction and in a reverse direction, right? You can put them together and you can make your one product, or you can take your product and you can split them up and turn them back into reactants, okay? In this lab, we will see how the initial concentrations of these products and reactants are affected or affect the equilibrium. Okay, as soon as I move this, right, my letters aren't going to move, so is it okay if I erase this? Yeah, okay, too bad. So materials, you're going to have 40 pieces of Lego. Inside each little baggie, there should be 40 pieces of Lego. Now, hopefully the previous class that did this, they were nice to you and they kept them together, okay? So you've got 20 products, but each product is 2 reactants, right? There's still 40 pieces, but they represent 20 products. What we want you to do is we want you to start with 20 products and no reactants. So start with them put together. Record your initial number of reactants and products on the back here. So that should be pretty easy, right? How many reactants are you going to start with in the first 0, right? And how many products are you going to start with? 20. Okay, sure, no problem. Record your initial numbers. Okay, then you have to start a timer, and you're going to start for 10 seconds. So let's kind of do this, okay? I need a volunteer, somebody who's not very capable with their hands, because I'm getting old, my eyesight's getting bad. I'm not a particularly dexterous person to begin with. Hey, Sky, come up here. You're totally going to whoop my butt, but that's okay. So we're going to start. Imagine there's a sheet of paper on the table, and the sheet of paper represents our beaker or our container. The Lego pieces cannot go outside the beaker, okay? I'm going to be either taking them apart or I'm going to be putting them together. Let's say I'm going to be putting them together. If I'm putting them together, what's Sky doing? Taking them apart, okay? We've got our 2 opposite reactions happening that are represented by this person. Now, a third or a fourth person in our group, they're going to be timing us every 10 seconds. So they're going to say, go, and then 10 seconds later they're going to say stop. And it doesn't matter if you're halfway through, you can't really be halfway through breaking apart, but whatever. You just got to stop what you're doing and you got to put them all together. What you're not allowed to do, and this is what some people in the other class were doing, is they were being super nice to their partner, okay? So for example, if I'm breaking these up, do I want to put them right in front of Sky, or do I want to put them back into the pile to make it harder for him to get at? I want to put them back into the pile. These represent chemicals. The chemicals are all mixed around together, right? So these chemicals should be all mixed in together. Is that okay? They should not be segregated. You shouldn't have one pile of reactants on one side and one pile of products on the other. Okay? What do you want to do? Do you want to take apart or put together? You're taking apart. I need somebody to time. Good. Max, awesome. Thank you very much. So sorry, what are you going to do? Take them apart?
Yeah.
Damn. Taking apart's way easier than putting together, but that's fine. Okay, so you, here in a second, once Matt is ready to have us time for 10 seconds. Are we ready?
Yeah.
Ready? Let us know.
Yeah.
And some of them are really hard to take apart. Yeah.
Stop.
I almost fell off. Okay, that's fine. So now what we have to do is we have to count how many products and how many reactants. Now, I know, just because you can kind of work out the math, each product is worth 2 reactants, okay? So I've got 4 reactants. That must mean we took apart 2 products. Does that kind of make sense? You don't really have to count them all up, but you can. So we've got 4 reactants. That means we must have 18 products left over. So I would put 4 and 18. And I would keep going. We want to keep going. Repeat steps 3 and 4. So starting the timer and recording your reactants and products until you've reached equilibrium. Now, what the hell does equilibrium look like in a chart like this? What is equilibrium going to look like in a chart like this? Once the numbers have stayed the same for maybe 2 or 3 rounds. Now here's the problem. I'm a human. Sometimes I'm going to be able to put them together really well, and sometimes I'm not. Same as Sky. Sky's going to be able to take them apart really well sometimes, and not at all on other times. I just need you to take this activity with a grain of salt, okay? You reach equilibrium once you have approximately the same numbers 2 or 3 rounds in a row. Does that make sense? We're trying to model that there's 2 opposite processes going on, and I just want you to have a little bit of fun with this. There's way more people than we have Lego pieces, so what you need to do is you just need to understand that there's not enough bags of Lego for all of the groups of like lab partners that we had yesterday. Is that okay? We need you to at least be in groups of 3, and I think we need 4 groups of 4. Is that okay? So if there's 2 of you and 2 of somebody else, then just make a group of 4 and go and start doing this activity at a sheet of paper. Do we kind of understand what's going on? Yeah. We're going to take, about half an hour for this. When you come back inside, there's questions on the back that I would like you to answer, like when you're done. I want to show you kind of what some people had gotten. This is the idea behind it. So, has anybody ever graphed anything in Google Sheets or Microsoft Excel or anything like that? It's phenomenally easy, would you agree? Especially compared to graphing by hand. Like, how much time, if you wanted to make a really high quality graph, how much time would you have to spend working on that graph if you were to draw it out by hand?
It would never take
Straight lines are
Okay, but I mean, in and around the order, JC, of about 10 minutes, right? Would you agree? Yeah, no, but like in and around the order of 10 minutes, because you got to figure out what the scale of the graph is, and you got to make your straight lines, and you got to make sure your data is plotted correctly, right? But here, I'm just trying to show you how nice it is to graph on a computer. All we have to do is I just highlight all of the information I want to graph. And I just go insert, chart, and it should, boom, should just show up, okay? So here, what do I want to do? Oh, here, I'm just going to zoom. Nope. Make that bigger. Get out of here. Okay, perfect. So this is the kind of information that some people got. And I want to be very clear about this, is that this information is brought about because we're human, because we Sometimes we work really well with the Legos and sometimes we don't. Also, not all these Legos are easy to take apart. Did you find that? Not all the Legos were nice to take apart. And that's only because I'm cheap and I bought like off-brand Lego. I didn't want to buy Lego. So I think it was like Roblox or something. I don't know, whatever. I don't know what the hell it was. Say so. But the key idea here, is if you were to graph this, do you know when we've reached equilibrium? Is it very obvious at what point in time we reached equilibrium? Yeah, here, right? Now, I want to show you an idealized equilibrium system. That's because you're human, and I don't mind having all of these problems with everything. I've got no problem with that. But I'm going to show you kind of what an idealized chemical reaction should look like. So go just insert chart, and boom. So here we've got our information. Right? It takes 20, 30 seconds, whatever, to be able to graph this. And this is very, very typical of the kind of equilibrium curve that we see. In the beginning, because would you agree, we only had products. We had no reactants in the beginning, right? So our reactant concentration is going to go up really fast, and our product concentration is going to go down pretty fast. For every one product that we lose, right? For every one product that we lose, how many reactants have we made? 2. So I don't know if you can tell, but the change in the products is half as big as the change in the reactants. Does that make sense? Because you're making 2 reactants for every one product. We'll talk about all the specifics of an equilibrium curve a little bit later, but I want you to be aware of what's going on. So there's going to be a steep curve at the beginning, and then it's going to slowly start to flatten out. And again, is it really obvious when we reach equilibrium? Yes. The point at which the number of products are no longer changing and the number of reactants are no longer changing. Right? That's what we care about. That's when we've reached equilibrium. So hopefully you're kind of okay with that. If you want to take this activity and you want to squirrel it away in your binder or whatever, that's totally fine. This was just an exploration activity. It's just for us to be able to understand a little bit more about equilibria. We do have some questions that we have to answer first, though. Okay, what are 2 important defining characteristics of dynamic equilibrium? Could anybody get one of the kind of the 2 important characteristics of a defining equilibrium? Well, yeah. Okay. So not necessarily this, right? But what's happening in a dynamic equilibrium? Are the particles, are the amounts staying the same? Yeah, but are they always the same particles all the time? No, so what I would say, probably the most important part of a dynamic equilibrium is that we've got 2 opposing or opposite, are we okay with that? 2 opposing or opposite reactions. And they're happening, that's a semicolon, that's just a really crappy semicolon. They're happening at the same rate as each other. I would argue that is the single defining feature of a dynamic equilibrium. This process and that process are happening at the same rate, so nothing's changing. Things are swapping sides, but as long as they swap sides the same amount, that's totally fine. What's a second important characteristic? Like, what kind of, oh, I don't want to give it away. What kind of, what do you have to have this happening inside? A closed system, right? So must be contained in a closed system. Hopefully you can read that. My letters tend to blur together when I try to go So explain how your results illustrate equilibrium has been established. Maybe you never once established equilibrium because you're humans and you're using crappy Legos, and that's totally fine. That's completely understandable. Maybe you never established equilibrium. But what I'm going to do is I want to delete this chart. I want you to focus on the information here. How can we tell when equilibrium is established? This is trial 0, 1, 2, 3, 4. So that's the trial number on the side. How would you know looking at this chart that equilibrium was established?
All the numbers are the same.
Sky?
Numbers are the same. For the reactant products.
Once the quantities of reactants and products start staying the same, right? Once we've established equilibrium, we have to do something dramatic to shift that equilibrium, to throw it out of equilibrium, right? Once we've hit here, we're in equilibrium. How do you know we're not at equilibrium as of trial number 2? How do you know we're not at equilibrium with 10 of these and 15 of those?
After that, it's 14 and 13.
Because if you wait a little bit more, they change. The quantities of them change. So obviously one of these reactions must be going faster than the other. Hopefully that kind of makes sense. Are we okay with that? I know I'm really sticking on this idea, and that's because it's a really important concept. We got about 10 minutes left. We're just going to talk a little bit more about a very specific equilibrium, if that's okay with you. Wait, did we ever answer that other question? No. Goodness gracious. What was that? Oh yeah, how do the initial concentrations of reactants and products affect the concentrations at equilibrium? We will talk about that later on, so I apologize, but unless you get really good results, it's really hard for us to model that properly, so we'll talk about that later. Okay, so here we have the exact same hydrogen iodide equilibrium that we had before. Okay, so we're gonna use some numbers to define this equilibrium. Now remember, what are the two reactions that are happening here? So we got hydrogen and iodine making hydrogen iodide, and then we've got the reverse of that process, right? Okay, so let's think about this for a second. I wanna take that, just draw like a dashed line there, and then let's draw another dashed line. And so these both, hydrogen and iodine, those are reactants, and our hydrogen iodide is products. This is our reactants, and this is our products. So what are we going on? Let's look at system number 1. This is our initial system concentrations. This is like if we had a container and we filled it with a little bit of hydrogen and a little bit of iodine. Did we fill it with any hydrogen iodide? Did we put any hydrogen iodide? No, we didn't. Okay. So we've got hydrogen and iodine, and they're free to react with each other. Then we let it establish equilibrium. We give it 30 minutes, we give it 10 seconds, we give it an hour, whatever, however long it takes to establish equilibrium. We let it establish equilibrium. What happened to our hydrogen and our iodine concentrations? From the beginning to the end, they decreased. Would you agree? Okay, so if they decreased, if our reactants decreased, what has to happen to our products? Increase, and indeed it did. Okay, perfect. That's fantastic. Let's look at a second trial, though. Instead of just starting with reactants, we could start with a mixture of reactants and products. So here we're starting with a mixture of reactants and a little bit of products. We give it a little bit of time, and what happens to our reactants? They decrease. Well, what happens to our products then? Increase. Okay, hopefully that makes sense. Now, did either of these times, in either of these trials, did we end up with completely 100% products? in either of these trials? Did we end up with completely 100% products? No. We always end up with a mixture of reactants and products in this reaction. Okay, well let's start with just products. We're starting with no reactants and just products. What's the only thing that can happen here? Our products have to decrease and they will turn into reactants. Is that okay? Yeah, okay, perfect. So 3 trials were performed and the concentrations of the chemicals are given above. What evidence is there to support that an equilibrium is occurring? Is there any evidence in here to support that there's an equilibrium? Remember, we put some reactants in a flask, and then 10 years later we came by, right? Did all of the reactants always finish up? Did all of the reactants always finish up? No. But we know there must be at least some forward reaction here. Do you agree? There's got to be at least forward reaction. Do you see any evidence of a reverse reaction happening here? Are trials 1, 2, or 3? I'm talking about all 3 trials. Trial 1, 2, or 3, do you see any evidence of a reverse reaction? Which reaction or which reactions are evidence that there is a reverse reaction going on? Does number 2 show evidence of a reverse reaction? No, because our products are being increased, right? But does trial number 3 show evidence of a reverse reaction? Yes. So that's what I would say. I would say, well, trial number 1 shows evidence of a forwards reaction. Trial number 1 shows evidence of a forwards reaction. While trial number 3 shows evidence of a reverse reaction. Does that sound like an equilibrium to you? There's evidence of both a forwards and a reverse reaction. That sounds like evidence of an equilibrium for me. So hopefully you're kind of okay with it. You got 5 minutes left. We're going to do a little tiny bit of math. Okay? Do not panic. Please do not panic, especially if you did not take Chem 20 with either myself, Miss Newton, or Mr. Zakowski. If you took Chem 20 with Miss Hagen or with Mr. Zielinski, we might do stoichiometry a little bit differently, okay? But let's just calm down. It'll be okay. Let's use stoichiometry to calculate the theoretical yield, the amount that we should have gotten in system number 1, in trial number 1, okay? So let's look at trial number 1. We start with both the same amount of hydrogen and the same amount of iodide. What is this concentration? 5 what?
Millimoles per liter.
Millimoles per liter. Okay, sure, no problem. 5 millimoles per liter. So let's think about this. We're starting hydrogen and iodine, and they're both gases. And it's turning into hydrogen iodide. And how many hydrogen iodides should be made here? 2. So if we start off with, what was that, 5 millimoles? 5 millimoles per liter. And I'm just going to put it under one of them, okay? We're just going to put it under one of them to really simplify things. Now, everything is being held by the same container, right? The volume that the hydrogen is occupying is the same volume that the hydrogen iodine is occupying, right? Because everything's all kept in the exact same container. So we've got some hydrogen iodide, but we also have some iodine. So it's the same volume, it doesn't really matter. I want you to just think about this rationally. If all of this turned into all of that, what concentration would we end up with for hydrogen iodide? Would you agree that we would end up with 10 millimoles per liter? Does that make sense? You just using your intuition? Okay? All right. If we wanted to prove it using stoichiometry, we totally could because the volumes are totally the same. We would say, what concentration measured probably in millimoles per liter of hydrogen iodide? This is how I do stoichiometry. We're going to get cut off halfway in about 40 seconds. But we're always starting with what we want. In my class, you can do stoichiometry however you want, but we're always starting with what we want. We want moles of hydrogen iodide, 2 moles of HI for every 1 mole of H2, and we're going to cancel that out with 5 millimoles per liter of H2 gas. So moles of H2 and moles of H2 cancel, and we're left with 10 millimoles per liter of HI. We'll come back to this tomorrow. We'll start talking about percent reactions, and we will do our ice tables, okay? Hopefully today wasn't super stressful. Hopefully nobody significantly injured themselves on the Lego blocks.
Sierra Car,